because these are proportionalities, we can just write T nu over T is equal to R nu to the 3/2 over RE to the 3/2. Since it's proportionalities, if we just divide one by the other, the proportionality constant goes away. And so we can therefore say 2T over T is equal to R nu to the 3/2 over RE to the 3/2, and we can go ahead and calculate the new Earth radius and find that the new Earth radius is equal to not the new Earth radius, sorry, the new radius of orbit is equal to, we cross multiply again, and we get 2 RE to 3/2 equal R nu to 3/2. Take the 2/3 power of both sides, and we get that the R nu equals 2 to the 2/3 times RE, which I think is about 1.6 times the Earth's radius. An orbital radius of 1.6 times the Earth's radius. So it's a 6/10 again as far from the surface of the Earth. So the new orbit would be 1.6 RE. So that's Kepler's third law. Let's move back to Kepler's second law. Equal areas and equal time, dA dt equals a constant. Kepler's second law. Just want to justify this one. There's a quick mathematical derivation we can do to justify this one. Let's look at the focus of the ellipse. The focus of the ellipse, the thing that's being orbited around, and some small area of which the thing that is orbiting is traveling through. So this is perhaps the sun, this is perhaps the Earth, or anything that is orbiting around anything. Let's say that it moves through some angle d theta, a small angle. If we make it infinitesimally small, then we can do this math quite easily. A small angle d theta, then in the time that it takes to move that small angle d theta, the Earth will move a distance, where r is the distance from the sun to the Earth, of r d theta. That's arc length, r d theta. The area of this triangle-ish kind of thing, it's got a curved end, but that curved end can be approximated as being straight if d theta is small. And when we're doing infinitesimal things, dA dt, then we can assume that they're so small that we can make these kinds of approximations. The area dA is equal to the 1/2 times the height times the width. 1/2 times r times r d theta. So dA is equal to 1/2 r squared d theta. So that's the area. In that infinitesimally small time, r does not change, but theta is changing, so we got d theta. So if we take the derivative dA dt on the left-hand side, on the right-hand side, the only thing that changes d theta, so d theta turns into d theta dt. So let's go ahead and rewrite that. dA dt, the time rate of change of area, or the amount of area being swept out, is 1/2 r squared d theta dt. Now, what is d theta dt? Remember back to rotational motion, d theta dt is just angular velocity, or omega, so it's 1/2 r squared omega. So dA dt is 1/2 r squared omega. And so now, if dA dt is a constant, 1/2 is already a constant. R is not a constant as we go around the ellipse. It was only a constant for that short time. So that means that r squared omega must be a constant. If dA dt is a constant, then r squared omega must be a constant. Well, is that really true? So if that's true, then we've proven Kepler's second law. Well, let's remember that if we have an object going around another object at a distance r, that it's got an angular momentum, L is equal to I omega. Remember, if you don't, that regular momentum or linear momentum is mv, and moment of inertia I is like m, omega, angular velocity, is like v, so angular momentum is I omega. And angular momentum is a constant if there are no net torques, and there are indeed no net torques when something is orbiting something. If that's not obvious, think about it, that the gravitational force does not exert a torque. So the angular momentum must be constant. If we treat these as point masses, right, so we've got the mass of the sun and the mass of the earth. If we treat these like point masses, then the moment of inertia, remember, the moment of inertia, L, is equal to mr squared. mr squared, m earth, r squared. That's the moment of inertia. The moment of inertia is the sum of all the point masses times their distance squared from the pivot point. mr squared, and omega is omega, right? So therefore, we actually have a term in here of r squared omega. My goodness, r squared omega. Whoops, that didn't look very good. But anyway, r squared omega. So we can solve for r squared omega just from angular momentum point of view and say it's angular momentum over the mass of the Earth if we're talking about the Earth going around the sun. I can go ahead and make that substitution back into the Kepler's second law derivation, or the dA dt derivation. So dA dt is equal to 1/2 of the angular momentum over the mass of the Earth. And so then the question is what's on the right-hand side a constant? And the answer is yes. Angular momentum is conserved, and the mass of the Earth is a constant, so dA dt is a constant. So we've proven Kepler's second law. So far we've looked at the gravitational force, or Newton's law of gravitation, GMM over r squared, from a Newton's second law point of view, a little bit of additional stuff, but we've really just been looking at the dynamics from force F equals ma point of view, and some kinematics. So now we really want to look at, so let's think about the potential energy due to gravity. The potential energy due to gravity near the Earth's surface, we already have dealt with many times. PE due to gravity is mgh. We know that, mgh. Well, what does that really mean? What we're saying when we say it's mgh is really that the change in potential energy due to gravity is equal to mg times change in h. And when we go from there to the first thing that I wrote down, we're defining h equals 0 somewhere. So we're saying when PE due to gravity is mgh, we're defining where the potential energy is 0. So usually what we do is we take the ground, and we say the ground, or the lowest level in the problem, we're going to say that's h equals 0. And then if we take an object and we lift that object up some height h above h equals 0, therefore the potential energy due to gravity is mgh. Well, so now I want you to think about, and we did this plenty last semester, what if we dug a hole? Let's leave h equals 0 at the ground, but we dug a hole. Let's go ahead and dig a hole in the ground, and let's make that hole some depth, whatever, it doesn't matter. We'll make it some depth, L. Let's call it L. So if I were to take my object and I drop the object, whoops, let's just take the same object with mass m. If I guess I never defined it having a mass m. Take my same object and I drop it in the hole, and then I ask, what is the potential energy of the object at the bottom of the hole? Well, the potential energy of the object at the bottom of the hole, if h equals 0 at the top, then it has to reduce in potential energy. The energy has to get smaller. So the potential energy of the object at the bottom of the hole is going to be mg times minus L, because it's gone down, or minus mgl. So it's going to be minus mgl. So wherever we define h equals 0, if we go above it, the potential energy gets larger. If we go below it, the potential energy gets smaller. If we define h equals 0, then if we go below it, the potential energy must be negative, right? But at any point, if you go higher, the potential energy gets bigger. If we go lower, the potential energy gets smaller. It's just that where we define h equals 0, then the potential energy must go from positive to negative. So what I want you to think about is actually, it's a negative potential energy is actually meaningful. to some extent. I mean, we always say you can always define h equals 0 where you want. If you define h equals 0 at some arbitrary point, then positive versus negative is not meaningful. But negative potential energies or negative total energies are actually meaningful if we define things well. So, for example, if I think about everything above the ground as being sort of this free space, but if it's in a hole, you're sort of trapped, right? You're trapped here. You're trapped in the hole. You're bound. Bound is the physics term we're going to use. You're bound in the hole. That just means you're trapped. How do we get out of the hole? How can I get the object out of the hole? I've got to give it enough kinetic energy to overcome the potential energy. The negative potential energy. So the total energy to get it out of the hole must end up being greater than 0, right? I've got to give it an amount of kinetic energy at least equal to that negative potential energy to get it up to h equals 0. So the total energy must be greater than 0 in order to get it unbound. This is meaningful in physics, is that we talk about bound states and unbound states. When you're bound, your total energy is less than 0. That means your potential energy has to be less than 0 when you're in a bound state, because kinetic energy can only ever be positive. So to be in a bound state, total energy must be less than 0. Therefore, since Ke is always greater than 0, therefore Pe must be less than 0. So we talk about, so we can define our h equals 0 to be a convenient place which tells us about what's bound and what's unbound. So in this case, for a mass on the ground, we think about something that we're trapped when we're in a hole, and we're not trapped when we're out of the hole. So we'll define h equals 0 at the surface of the Earth, and so that'll define our bound versus unbound states. And actually, and that's perfectly fair for things near the surface of the Earth. But when we're talking about gravitation at a larger scale, we're actually going to define our h equals 0 slightly differently. To talk about when things are bound, in this case in orbits, versus when they're unbound in orbits. So in the case of the gravitational force, F equals G m1 m2 over r squared, if we're talking about, let's say, the Earth is m1 and some object that we're holding above the surface of the Earth is m2. Okay, I'm not sure what I just said, but the force of gravity of some object m2 above some near some object of mass m1, their centers are separated by r, is gm m1 m2 over r. This could be a mass above the surface of the Earth. It could be the Earth relative to the Sun, whatever, two masses. And if we wanted to define the potential energy of the m1 m2 pair, remember potential energy is defined from the work, wrong pen. The work is equal to the integral of f dot dr, which equals minus the change in potential energy. So when we were talking about the force of gravity near the surface of the Earth, F was just mg. So dr just became h, and so it was mgh. But now we're talking about a force which has a different form, a different relationship to distance, and so we've actually got to do this integral. Whoops, I forgot to write r squared over here. So the way the signs work out is a little bit complicated here. We've got a bunch of negative signs because this is a vector equation. Work equals F dot dr is a vector equation. Remember, F has a direction of minus r hat. Dr has a direction of r hat. So we can rewrite this as the integral of g m1 m2 over r squared times minus dr hat dotted with dr times r hat. That's a little messy. So I rewrote it over to the left. So taking into account, these are vector equations and this is a dot product. So the direction of the gravitational force is in the minus r hat direction. The direction of dr is in the plus r hat direction. That's the second line over here. And the first line was what I read. And so that means that the work can be written like this when we get rid of the dot product. So now we have to take the integral of gmm over r squared dr from where the potential energy is 0, I'm just going to write from 0, to some radius r. Now, where is the potential energy equal to 0? Maybe 0 was the wrong thing to write there. It should have been PE equals 0, from the position at which PE equals 0. Now, where is the potential energy equal to 0? We can define it, remember, where the potential energy is equal to 0, but there's a convenient, mathematically and physically convenient place where the potential energy is 0. Where does the gravitational force not impact a body at all? When does the gravity go away? The gravity goes away when r equals infinity, when we're infinitely far away from the planet. Therefore, the force due to gravity is equal to 0. That is the only place that the force due to gravity is equal to 0. That doesn't mean we have to define potential energy equal to 0 at r equals infinity, but it's a good place to do it because also the discussion we just had about bound states, the only time that M2 is not going to be bound to M1 by gravity is when it's infinitely far away. So we'd like the potential energy to always be negative, and the potential energy will always be negative if we make potential energy equals 0 at infinity. And so then as we get closer to the Earth, just like when we went down that hole, as we get closer to the Earth, the potential energy is going to get more and more negative. So it makes the most physical and mathematical sense to set the potential energy equal to 0 at r equals infinity. Right? I mean, mathematically it makes sense because if I put r equal infinity in the bottom of the force equation, that's when the force goes to 0. That, therefore, is also when the potential energy goes to 0. So we're going to go ahead and do this integral from infinity to r, and what we end up getting is, therefore, the work to go from infinity to r is plus gm1 m2 over r. That's when we do the integral. We can even say from infinity to r, and we evaluate it, and so that's the work. And the work, remember, is minus the change in potential energy. So therefore, the potential energy at a position r is equal to minus g m1 m2 over r. This is the end result, where PE at infinity is equal to 0. So potential energy at a position r is minus gmm over r. Potential energy at infinity is equal to 0. So regardless of the derivation, we are defining the potential energy at a radius r from the surface of the Earth, right? Or can exist for any two things, right? So for M2, the Earth is M1. Did I say from the surface? From the center of the Earth, that the potential energy at that point is gm1 m2 over r, minus gm1 m2 over r. The potential energy relative to the potential energy at infinity is 0. So that's just always going to be implied, that the potential energy at infinity is 0. So the closer you get to Earth, the bigger the negative potential energy, and at the surface of the Earth, the potential energy is not 0. At the surface of the Earth, the potential energy is gm1 m2 over r Earth. So there's nothing new here. Don't be confused by this, right? We still do energy conservation problems exactly the same. Let's say that I have an object of mass m above the surface of the Earth, and now we're measuring distances from the center of the Earth, because that's what we do with gravitation. And so let's just say that it's above the surface of the Earth, and it could be just h above the surface of the Earth or something, but let's say that it is h equal to, now let's make it an astronomical distance, like 1/2 the radius of the Earth above the surface of the Earth. So it's 1/2 the radius of the Earth above the surface of the Earth. That means from the center of the Earth, the radius vector is equal to RE plus 1/2 RE, right? So let's take an object up. 1/2 the radius of the Earth, 3,000 meters up, or whatever that is. And let's drop it and ask how fast is it moving at the surface of the Earth. So if I drop it from rest, how fast is it moving at the surface of the Earth? Well, so we're just going to do this as an energy conservation problem. We're going to say PE initial plus KE initial is the total mechanical energy at the highest height. PE final plus KE final is the total mechanical energy at the lowest height. And right, how fast will it hit the ground? Move when it gets to the ground. Move. Will it be moving at ground before it hits the ground? So we're going to conserve energy. So whoops, sorry, that was messy. Oh, crumbs. All right. So EI equals EF. So PE initial minus GM M Earth over R initial plus KE initial, 0, equals PE final minus GM M Earth over R final plus K final, 1/2 M. I ran out of space. Darn it. I'm going to rewrite this on the next page. Okay, I've rewritten it on the next page. One thing I want to point out, really important here, is that this is potential energy. So this is R, not R squared. It is so easy to forget whether you're talking about potential energy or force, but you just need to think about the context. This is potential energy, and so this is GMM over R, not GMM over R squared. So this is just an energy conservation problem. RI, RF are given to you, right? So RI, let's find the same color. RI was RE plus 1/2 RE. R final, it ends up at the surface of the Earth, so RE. And so therefore we can just, it's a plug-in, GMME over 3/2 RE is equal to, whoops, there's a minus sign, minus GMME over RE plus 1/2 MV final squared. So solving for V, we get 1/3 GME over RE. Yeah, it's just a regular energy conservation problem. We could plug in numbers, right? It's independent of the mass of the falling thing, just like it's always been. We could plug in numbers and figure out what that velocity would be. So let's go ahead and look at the energy of something in orbit. Something in orbit, let's again take the Earth and a satellite at some R greater than RE, and look at, we might have to define R, I'm not sure yet, and let's look at the energy of orbit, the energy of something in orbit. Well, the energy of something in orbit is going to be minus GM of the objects in orbit, M of the planet that's orbiting around, times the radius of the orbit, plus 1/2 mv squared. But we know from Newton's second law what the velocity or the speed is. I've just written down what we had done numerous times previously. From Newton's second law, GMM over R squared equals mv squared over R. We can find the speed, and so therefore we can write the energy of something in orbit, the total energy of something orbiting, minus GMME over R plus 1/2 mGME over R. So that ends up being that the energy of something in orbit, anything in orbit, is minus GMME over R. Whoops, over 2R. 1/2 GMM over R. Just solve the algebra from the previous page, and that's what you get. That the total energy of something in orbit is minus GMM over 2R. What this tells you, what's important here, is the negative sign. The negative sign means that it's bound. It's bound in orbit. It hasn't escaped. It doesn't have enough energy to escape. That is for something that is in a stable orbit. If you want something to escape, you need to get its energy greater than zero, right? The energy, that's the whole point of the discussion we just had about negative signs, is that a negative total energy means that it's bound, and a positive total energy means that it's unbound. So we would have to give it more kinetic energy to get it out of that orbit. Enough kinetic energy, we'd actually have to give it this much kinetic energy in order to get out of that orbit. So we can talk about the same concept with something that's not in orbit, right? So let's take a rocket. Well, that doesn't really look like a rocket, but let's pretend it's a rocket. A rocket on the surface of the Earth, and ask, how fast do we need to shoot that rocket off in order to get it unbound so that it's not stuck to the Earth, so it can just keep going, so it won't fall back down? Well, that's a pretty easy question to answer, because if we at the surface of the Earth, if the potential energy is minus g m rocket m Earth over it's at the surface of the Earth, our Earth, then we need to give it that much kinetic energy. We need to give it that much kinetic energy in order to get it unbound from the Earth. So we need to overcome the total energy of the total energy has got to be greater than zero. So we need to give it a kinetic energy of at least g or greater than g m greater than or equal to g m of the rocket, m of the Earth, r of the Earth, in order to get it unbound from the Earth. And what I mean by unbound is if we give it any less than that, it's going to fall back down to Earth eventually, which we pretty much want our rockets to do, but not always. We've had rockets that we want to keep going, and so we've got to give them enough energy to escape the Earth. It's called escape velocity when we figure out how fast it has to go to escape the Earth. So this would be 1/2 m rocket v squared, and we could figure out what the escape velocity is. So I just went ahead and solved for v from kinetic energy equals 1/2 mv squared, solved that equation, and I get 11,208 meters per second, or about 20,000 miles an hour. So if we can send a rocket off with a speed of, or a projectile off the surface of the Earth at 20,000 miles an hour, it's going to go fast enough that it'll keep going, it'll never come back. Anything slower, it'll go up, come back down. So to summarize, the potential energy due to gravity is now minus g m1 m2 over r for the potential energy for any two objects in the vicinity of each other. The kinetic energy is still 1/2, as always, 1/2 mv squared, and so the total energy of any object is Pe plus Ke, and given the situation, we showed that was, for example, equal to minus g m me over 2r for something, special case of an orbit. And I did the orbit for mass m orbiting the Earth but at an orbital radius r from the center of the Earth, but it could be any one object orbiting a second object. And the last point is that the negative sign is meaningful. If the total energy is negative, it means it's bound. It's in a bound state. And if the total energy is positive, it means that the two objects are not bound to each other and can escape from each other.